So the today problem is binary tree preorder traversal. And it's pretty simple. We're traversing through the tree and returning the values. A preorder traversal is the root and then the left node and then the right node. A post-order traversal is the left node and then the right node and then the root, or the left subtree and then the right subtree and then the root's value. An in-order traversal would be the left value, the root value, and the right value. And even in that explanation, you kind of get a sense that you really only need the relationship between the root, the left, and the right. And that applies not only to a base case of, for example, if you only had 3 nodes, if one dot left was 3, and this was like a very basic tree. And it also is true for a giant structure with a depth of 1,000. There's sort of a fractal nature to not only trees, but the algorithms that traverse them, which means that they're relatively elegant once you cut away the chaff. So we'll start and we'll say st equals dq, and then we'll just put the root in it right away. dq in Python is the stack and the queue. I think it means double-ended queue, but we're using a stack this time. If we did something like a level order traversal where it's the top level and then the second and then the third, then we would want a queue. But a stack is kind of for these depth first search-esque things. And then we'll say ands is an empty list, and then in the end we're going to return ands. And then here we'll have a while statement, while stack, and then we'll say cur is stack.pop. So now we put root in the stack, we're immediately popping root in the first iteration, or in the first iteration of this loop. And then we'll say something like if cur is none, continue. So for example, if root was none, if we're given nothing, we'll just return an empty list. And then we'll say ands.append cur.val, because we're appending the root value first, and then we're appending the leftmost value, or we're sorting out the left subtree and appending all of those values. So then we would say, we actually would want to say stack.append cur.left, but we actually want to append the right one first. And this is sort of a quality of stacks where we're putting the right node on top. So we're saying, okay, sort through the right subtree. And then immediately after that, we're putting the left node on top, and we're saying, actually, before you do that, now there's something else covering that. Do the left subtree first. And this works. I mean, realistically, this is a conceptual problem. It's just figuring out what a preorder traversal is, looking that up and being like, oh, that's the order for that. Pretty much any submission is going to be O of n. I would be very surprised to find a submission that's all that much quicker or slower than this. But looking at these submissions, it seems like if you do something recursive, it's slightly faster, and you can kind of get away with sort of only using O of 1 space complexity instead of this being O of log n space complexity. And that's just doing it recursively. So instead of this, we'll keep this. So we're basically just going to take everything out of this loop, and we're going to put it in the normal function. And then instead of having a loop, we're just going to have the function call itself. So we'll say something like, if root is none, return an empty list. And then we'll also put, I looked at the top submissions, and it seems like they kind of covered this corner case. Is none and root.right is none, return a list with root in it. And we actually want to have root.val. So the idea is if root is none, just return nothing. Also, if it's a leaf, just return only its value in a list. And then we're going to say return, then we want to say root.val plus preorder traversal of root.left plus preorder traversal of root.right. Oops, self dot. So this is, I mean, again, almost exactly the same, but if you wanted to do a recursive solution, this would be it. Typically, hiring recruiters and stuff prefer iterative because it messes with the call stack less than a recursive solution would. And also this is a little more conceptually complicated, that we're kind of manipulating lists and adding lists to other lists and stuff. But that's an iterative and recursive solution to this.